Electromagnetic radiation and its role in remote sensing. Remote sensing, a cornerstone of modern geospatial analysis, relies fundamentally on the principles of electromagnetic radiation, EMR. This invisible thread weaves through various disciplines, enabling scientists to collect, interpret, and apply data about Earth and other planetary surfaces. Understanding the role of electromagnetic radiation in remote sensing unveils the technology's sophistication and its vast applications. What is electromagnetic radiation? Electromagnetic radiation refers to the energy propagated through space as electric and magnetic fields oscillate perpendicular to each other and to the direction of wave propagation. EMR spans a spectrum of wavelengths and frequencies, from gamma rays to radio waves, classified into regions such as ultraviolet, visible, infrared, and microwave. The diversity of wavelengths allows remote sensing to capture a wide range of phenomena. Interaction with Earth's surface. When EMR encounters Earth's surface, it interacts in three primary ways: absorption, reflection, and transmission. The proportions of these interactions depend on the surface material and the wavelength of the radiation. For example, vegetation strongly absorbs red and blue light for photosynthesis while reflecting green and near-infrared wavelengths. Water absorbs most wavelengths except for a narrow band in the blue-green region, explaining its color in natural light. Urban areas reflect differently across the spectrum, depending on materials such as concrete, metal, and asphalt. These interaction patterns form the basis for distinguishing features in remote sensing imagery. Remote sensing platforms and sensors. Remote sensing systems use sensors mounted on platforms such as satellites, drones, or aircraft to detect and measure EMR. These sensors are typically categorized into two types. 1. Passive sensors depend on natural energy sources, primarily sunlight, and measure reflected or emitted radiation. Examples include Landsat's Operational Land Imager, OLA, and the Moderate Resolution Imaging Spectroradiometer. 2. Active sensors emit their own energy and measure the reflected signal. Examples include radar systems like Sentinel-1 and LiDAR technologies. The choice of sensor depends on the application, whether monitoring vegetation health, mapping urban growth, or studying atmospheric conditions. Applications of EMR in remote sensing. Electromagnetic radiation underpins countless remote sensing applications. Some key examples include environmental monitoring, identifying changes in land use, deforestation, and water quality. Climate studies, measuring sea surface temperatures, ice cover, and atmospheric composition. Agriculture, assessing crop health and yield predictions using multispectral and hyperspectral data. Disaster management, supporting rapid response during natural disasters like floods, wildfires, and earthquakes. Advancements in future trends. Emerging technologies are enhancing the capabilities of remote sensing. Hyperspectral imaging, with its ability to capture hundreds of narrow spectral bands, provides unprecedented detail about surface materials. Advances in machine learning and artificial intelligence are transforming the interpretation of remote sensing data, enabling faster and more accurate insights. Moreover, the miniaturization of sensors and platforms, including CubeSats, is democratizing access to remote sensing technology, expanding its reach to new sectors and applications. Electromagnetic radiation is the lifeblood of remote sensing, making it possible to observe and analyze the world in ways that were once unimaginable. As the technology evolves, it continues to unlock new dimensions of understanding, driving innovation across fields ranging from environmental science to urban planning. By harnessing the principles of EMR, remote sensing remains an indispensable tool for addressing global challenges and advancing scientific discovery.